to now, we've taken as a reference cycle for gas turbine cycle a closed cycle with external combustion. This is due to the fact that it's easier to describe from a thermodynamic point of view. Let's now look at open cycles with internal combustion, because those cycles with internal combustion are the most common gas turbine cycles. So when we have internal combustion, so it means that inside the fluid, the working fluid that is following the different transformation in the system, inside this fluid there will be combustion, and this combustion will directly increase the temperature of the high pressure gas instead of having a heat exchange in a heat exchanger with a hot source. So in that case, at the inlet of the system, so at low pressure and low temperature at the inlet of the compressor, so it means here we have an open inlet. It's usually air taken from the environment, so around 1 bar and 20 degrees Celsius when it's at ground level. But if we use this kind of machine at higher altitudes for airplanes, it can lower the pressure and also lower the temperature of the ambient conditions. So this air, which is a combustive, is compressed alone in the compressor, and so it goes out of the compressor at a higher temperature and also at high pressure. This high pressure air is sent to the combustion chamber, and in this chamber the fuel is added. This fuel is added at high pressure too, and combustion takes place in the combustion chamber. Combustion is an exothermal chemical reaction, so all the heat that is released by the chemical reaction will be used here to increase the temperature of the smoke. So the smoke, that's the name for the product of this combustion reaction. And in the combustion chamber, as for a heat exchanger, we can consider, at least at first approximation, that it's an isobaric transformation. So then we get the smoke at high pressure, high temperature, and this smoke is sent to the turbine, will be expanded in the turbine down to inlet pressure, so atmospheric pressure, and then the low pressure smoke is just sent to the exhaust, released to the atmosphere, and so that's an open cycle. We don't reuse the fluid that passed once through the cycle. So there are several changes that can be noted. Because we have internal combustion, there's a change of material, so we cannot have a closed cycle, we need to have an open cycle. And because we have an open cycle, one of the transformations is completely removed. There's no need to cool down the exhaust smoke down to the inlet temperature, because we take fresh air which is already at low temperature. So we don't need to have this heat exchange with the cold source in this case. So the question now is, from a thermodynamic point of view and for the analysis of this cycle, what are the differences between this cycle and the closed cycle we have been studying, and also what are the consequences of these changes. So here I would like to mention mainly two big differences. The first one is that the mass flow rate is not everywhere the same, because here we have a mass flow rate of air which is mixed with the mass flow rate of fuel, and so the mass flow rate of smoke that will be expanded is the sum of the mass flow rate of air that has been compressed in the compressor plus the mass flow rate of fuel. So that would be the first difference. The mass flow rates are not everywhere the same. Second big difference we have between this internal combustion cycle and the closed cycle is that the nature of the fluid is changing. Here the air is compressed, but then it's the smoke that is expanded, and the smoke has a different chemical nature due to the chemical reaction that took place in the combustion chamber. So there's a change of chemical nature of the fluid. So the question is, what does it change for the thermodynamic analysis? Here we can do two remarks before going further. The first remark is that the combustive is not directly dioxygen, which is used for the combustion of the fuel, but it's air. And air is a mixture of many different gases, but mainly 76% of mass of nitrogen and most of the rest of dioxygen. So it means that 3/4 of the air is not even taking part to the combustion here, and so will be unchanged in the mixture of gases that is present in the smoke. So we can first think that 76% of air is made of N2. Then there's a second remark. It's about the excess of air. In an internal combustion gas turbine, it's not possible to do the combustion at stoichiometry. So let's first define what is stoichiometry. Stoichiometry is the exact proportion of fuel and combustive so that all the fuel will be burnt and all the dioxygen from the combustive will be used for this reaction. So in the smoke there will be no more dioxygen. What is present in the smoke is mostly CO2 and water that comes from the carbon and hydrogen of the fuel, and then there will be the nitrogen that was unreacted as main components of the smoke. The problem if the combustion is done at stoichiometry is that there's a considerable amount of heat that is released by combustion, and it will heat up too much the smoke, and the smoke temperature will be way too high compared to what is possible to admit at the inlet of the turbine. For this reason, the gas turbines are working with a quite large excess of air, so there will be more air than the necessary air for the combustion, and so there will be even more nitrogen that will be unreacted in the smoke, but also some remaining of O2 that will be also unburned. And due to this presence, because the combustion also has to heat up not only the normal smoke but also the excess of air that is mixed with it, then the smoke temperature at the outlet of the combustion chamber will be lower. So that's the second thing we can say, there's a large excess of air for the reaction. And so if we take these two remarks and look at these two differences, because most of the flow rate is made of air, this is due to the fact that a lot of the air is not reacting at all, and also due to the excess of air, this is even increasing the amount of this mass flow rate that is not taking part to the combustion, it means that most of the mass flow rate is air, and the mass flow rate of fuel is really small compared to the mass flow rate of air. So this can lead to a reasonable approximation that the mass flow rate of smoke is almost equal to the mass flow rate of air, and so we can reasonably neglect the change of mass flow rate due to the fuel addition in the combustion chamber. A second thing we can neglect, and for exactly the same reason, is the change in thermophysical properties of the fluid, because most of the smoke in fact is still exactly air like it was before the combustion chamber, I mean. So there's especially one thermophysical property that is of interest for us. It's the CP, the specific heat capacity at constant pressure, because it's directly related to the enthalpy variations that we have been calculating, and because the smoke is so close to the air, we can also reasonably do the approximation that the Cp of the smoke is equal to the Cp of the air. And this is especially true because what is causing the biggest variation in Cp are the temperature changes that we have in this cycle, a lot more than the change of chemical nature of the fluid. So what can we conclude from this approximation? So simply that an internal combustion open gas turbine cycle can be treated as if it was a closed cycle, and all the developments that were made before for the external combustion closed cycle is still valid for this kind of cycle.